Solving for the value of pi is essentially a two-step process. The first step is to cut a 1 unit diameter circle and then measure its pi circumference. Everybody remembers that the circumference of a circle is C for circumference equals diameter times pi. And if we let diameter equal to 1, then the circumference equals 1 times pi, and 1 times any number is that number, and that equals pi. So the circumference of a 1 unit diameter circle is going to be pi. That's the first step. We already did that. We measured it with a tape measure, and we found out that the circumference was, in our measurement, 3.1446, as close as we could get it. It certainly was not 3.1416. We definitely proved that it's not this guy, it is this guy. So let's go to step 2 and let's learn how to square the sides of a Kepler golden ratio right triangle. In step 2, in solving for the true value of pi, we already know that pi out to the 4 decimal places by laboratory measurement is 3.1446. That's as close as we can measure it physically. Now we want to prove it mathematically. And the way we're going to prove it mathematically is to square each side of Kepler's triangle. So what is Kepler's triangle? Kepler's triangle is named after the famous mathematician Johannes Kepler, who lived in the 1600s. It's a special right triangle. It's a golden ratio right triangle because its sides are in the golden ratio relationship with sides equal to 1 square root of phi, and the hypotenuse is phi in our example here. Numerically, the golden ratio phi is equal to 1.618033989. That's out to 9 decimal places. And it's represented by the Greek symbol phi, or it looks like a 0 with a line through it. It is phi. The square root of the golden ratio is equal to 1.272019650 out to 9 decimal places, and it's represented, of course, by the symbol, the square root of phi. The 3 dots after those numbers mean that it goes on forever. That is an irrational number, and number is not the ratio of 2 integers. So you might ask, what's the golden ratio? It's a relationship whose number differs from its reciprocal by 1, which means the product and difference vary by 1. Symbolically, the golden ratio is defined as a number, phi, minus the reciprocal of phi equal to 1, and at the same time, phi times its reciprocal also equals 1. It's a very special number, the only one in the universe like that. So looking at the Kepler triangle here, we notice that the hypotenuse is phi, the next largest side is the square root of phi, and the smallest side excuse me, is 1. When we say, let me back up. Of course, Kepler's triangle follows the standard Pythagorean theorem, where the square of the hypotenuse equals the sum of the squares of the sides. So c, in this case, c squared equals a squared plus b squared. That was true, Kepler knew that, but what else Kepler discovered was that a times c, the smallest side times the hypotenuse, equals the other side, b squared. And you can go through the calcs if you want and see that. That's what Kepler discovered. What I recently discovered, and have no idea if anybody else has come up with this relationship, is that you can square each side of Kepler's triangle to its next largest side, the circle to the square, and the circumference of the circle will equal the perimeter of the square. Once you do that, you have eliminated the problem of the circumference, determining what it is, and you can equate the equation for the circle equal to the equation for the perimeter of a square. The circumference of the circle will equal the perimeter of the square, and thus you can then solve for the value of pi. So let's solve for the first case, I call it each of these three cases, for squaring the side of Kepler's golden ratio right triangle. If you take the hypotenuse C and multiply it times pi, that circumference, that will be a circle, because pi times any straight line number is going to be a circle, that will equal 4 times b. b, of course, is the square root of phi. 4 times a straight line number is a square, so we are essentially squaring a circle to a square. And let's take a quick look at that. We already know pi out to 4 decimal places. As you can see in this equation here, pi times c equals 4 times b, circumference equals perimeter, or pi times phi equals 4 times the square root of phi. Reducing that equation, pi equals 4 divided by the square root of phi. Using only 4 decimal places, since that's all we know right now for pi, we see that the circumference is 5.0880, and the perimeter is also 5.0880. We can go ahead and multiply the square's perimeter all the way out to, I did 30 here. In the written proof, I carried it out to 40 decimal places. And you can see we get this long number out to 30 decimal places. And if we go ahead and substitute the value for pi that we've solved, dividing 4 by the square root of phi, that's a long number, I've shown you 30 decimal places here, and multiply that pi times the hypotenuse, c, we get the same number for the circumference that we got for the perimeter, all the way out at every decimal point to 30 places. We have essentially, and I've carried it out to 40 places, we essentially have shown that the circumference equals the perimeter out to 30, 40 decimal places, and what you see, 3.144605511029693, blah, 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 equals pi. That's case 1 for the hypotenuse. We squared the hypotenuse to the other side, the second largest side, to equal the perimeter of that square. So what you see here is the green circle circumference equals the perimeter of that red square. Now we can do this for every side of Kepler's triangle. Let's go to the next side. Let's multiply pi times the red line. That's going to be a circle. In fact, it will be this red circle. It will be the circumference of that circle, and that will equal 4 times the third side, which is 1. What we've done once again is, let's look at the equations. First the circle, the red circle, circumference equals the perimeter of the purple perimeter of the other side, the short side. And what we have done, once again, just like we did in the first case, is we have multiplied pi times b equals 4 times a, or pi times the square root of phi equals 4 times 1. Solving for pi, once again, pi reduces to 4 divided by the square root of phi, in this case 2, just like it did in case 1. The circumference, we know. First, let's look at the perimeter. The perimeter is 4, because 4 times 1 is 4, and carry that out to 30, 40 decimal places. If you multiply pi the long pi that we have even, and we know it out to 4 places, which is why I show in red 4.0000. We know that for sure. And if we multiply the square root of phi, big long number, 1.272, blah, 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 times pi, 3.1446, multiply those 40 digits of pi times 40 digits of the square root of phi, we get for circumference 4 exactly out to 40 decimal places. So for case 2, we show pi equals 4 over the square root of phi. So now let's look at the third case for squaring this last side of the Kepler triangle. I call it case 3. And of course that is pi times a equals 4 times the ratio of a over b. It also equals the ratio of 4 times b over c. It's a very interesting phenomenon. Looking at the equal circle, the circumference of the circle in this case 3 equals the perimeter of the square. Once again, we already knew pi out to 4 decimal places, 3.1446 by laboratory measurement, and by now case 1 and case 2 we're showing that when we equate these two equations, and there's 2 of them for this side, and solve for pi, pi reduces once again to 4 divided by the square root of phi. Going through the calculations here, we multiply pi times 1, which is of course pi, and in the other equations, 4 times 1 over the square root of phi also equals 4 times the square root of phi over phi. So we have shown in all 3 cases, squaring each side of the Kepler triangle, the golden ratio right triangle, that pi always equals 4 divided by the square root of phi. And you can see the number for pi there. This is of course much larger than what we could measure. Anyway, that's the second part of solving for pi. The fact that we had the initial measurement of cutting a 1 unit diameter circle and then measuring its pi circumference and then using that as a basic starting point to do the proof for Kepler's special triangle by squaring each side brings us to the conclusion that pi really is 3.144605511, etc., and pi is not 3.1416. So now that we've proven the true value of pi in 2 different ways, number 1, we measured the pi circumference of a 1 unit diameter circle and found out that pi out to 4 decimal places is 3.1446, and that it definitely is not 3.1416. The second method was that we used Kepler's golden ratio right triangle to square each side of Kepler's triangle, equating the circumference of each side's circle to the perimeter of the next largest side's square. And we did that all the way around in 3 cases to show that pi equals 3.1446, and carry that out to 30 places, actually 40 places, decimal places, because we can reduce in each case the equation to solve for pi to 4 over the square root of the golden ratio. Now we have a third interesting phenomenon, a curiosity we'll call it, and that is we're We're going to square the area of the circle using 8 Kepler golden ratio right triangles. So how do we do that? You can see right here that we have 8 Kepler triangles. 1, 2, 3, 4, 5, 6, 7, 8. And in each case, the sides are 1, square root of phi, and phi for those triangles. Then we drew a circle with a center at y. The center has a radius of the square root of 5. What we're going to do is calculate the area of ABCD, rectangle ABCD, and that is simply 2 times 2 times 2 times the square root of phi. That equals 5.088076 square units. If we calculate the area of the circle, pi r squared is simply pi times the square root of phi squared. Square root of phi squared is phi. We already know that phi times pi equals 5.088076 from previously in proof 6, in which we calculated the circle with a diameter equal to the hypotenuse of Kepler's triangle. So the amazing thing here, the curiosity here, is that by squaring this rectangle ABCD with these 8 Kepler triangles, we equal the area for this rectangle to the area of the circle. Essentially, we have squared or rectangled, if you like, the area of the circle y to rectangle ABCD. And if you really want to know the square area, you simply take the square root of the area ABCD, and of course that side of the all 4 sides of that square would be 2.255676972 carried out to 9 decimal places. So just using a straight edge and a compass, we indeed can square the circumference of a circle to a square, to the perimeter of a square. We can also square the area of the circle to the area of a rectangle, and thus do a simple math square root to get the length of each side of the square. So obviously in the first instance, we're talking linear units using circumference and perimeter, and in this curious case the units are square. But the amazing thing is that they're the same numerical values, 5.088076. Another curiosity in the ongoing saga of finding true pi. In order to re-emphasize how important it is to physically measure the pi circumference of a 1 unit diameter circle, in order to get a start to discovering what true pi is out to 30 and 40 decimal places, it is very important, because if you use the old value of pi, as we can see in this table here, what is this table? This table is a comparison of squaring each side of Kepler's golden ratio right triangle, whose sides are in the order of 1, square root of phi, and phi, which is the golden ratio. And we have 3 cases in which we are claiming that if you use the correct value of pi, then pi times each side equals 4 times the length of the second largest size to that. And you can carry that through case 2. Pi times b equals 4 times a, and pi times a equals 4 times the ratio of a over b, which equals also the ratio of b over c, 4 times that. So if that is true, and we know it's true for 4 decimal places at least, we can then simply solve each equation after equating circumference to perimeter and solve for pi. And in every case, pi equals 4 divided by the square root of the golden ratio, which is 3.1446, which is as far as we can measure it, but we can then compute that large value of pi, and I computed it out to 40 places in the proof, so that this is true. That is the circumference using Harry's pi, 3.144605511 out to 9 decimal places. The circumference equals the perimeter. And if you carry that out to 30, 40 decimal places, you will find that in the first case, the numbers 5.0880, etc., are exactly equal. The same for the second case, in which the circumference equals the perimeter of 4.000 out to 30, 40 decimal places. In the third one, the third case in our discussion here of squaring the sides, the circumference is 3.144605511, which happens to be pi, and so is the perimeter. It's pretty simple. But if you use the old pi, which is an approximation using Archimedes' old methodology of trying to circumscribe or inscribe, or rather I should say and inscribe, regular polygons outside of and within a given circle, that you're going to come close to discovering the pi circumference. That's correct. You'll come close, but you're going to be off at the third decimal, both in the case 1, case 2, and case 3 of squaring the sides of Kepler's triangle. You can see that they're too short. That's because the old pi is too short. It's too short by 0.003. We discovered that both by physical measurement, and we have also discovered it by, right now, through mathematical computations. So my advice to all you mathematicians, all of you engineers, physicists, I don't care if you work for NASA, I don't care which university you're at, please go cut a 1 unit circle, 1 meter diameter, and measure the pi circumference. You will discover, if you do it correctly, that you will pi will be 3.1446. Then just do these calculations for squaring the sides of Kepler's triangle out to 4 places, and then solve, equate the circumference to the perimeter, and solve for pi. Solve it out to 40 decimal places. Then substitute those 40 decimal places for pi into these equations, and when you multiply 40 decimal places worth of pi times 40 decimal places of phi, and you get exact equation for circumference and perimeter in all 3 cases, especially the middle one, which is 4 out to 40 decimal places, and there are some humongous numbers there that will equal that exactly. You know that you have discovered what pi truly is. And so I really urge you to go do the physical measurement, then go do the math, and you will come to the same conclusion. That's just a little additional information I wanted to provide to you. We've shown this in earlier videos from a different approach, but this is the math proof for what we found in the laboratory.